How do you represent negative numbers in binary? This is a question I'm sure you've been asking yourself, and today you're going to find out. Let's say we're using 4 bits to represent all of our binary numbers. Now, in reality, most computers use 32 bits or even more to represent their binary numbers, but we're just using 4 to keep it simple. So on the very bottom here, I have represented the number 0, and I'm going up the number line like this, and I'm representing 15 on top. Now, these are all positive numbers. Now, if we decided that we wanted to make negative numbers, we have to split our numbers in half, and usually they're split right down the middle here. The first bit is called the sign bit. So in this case, my most significant bit is right here, and these are all ones, and a 1 represents negative. A 0 on the bottom, I have zeros in my most significant bit place. These represent positive numbers. So again, all my negative numbers are on top, all my positive numbers are on the bottom, and I'm obviously going to have to renumber these. These are going to be all negative numbers. So the question is, which one should be -1? Should this guy be -1? Should this guy be -1? Maybe this guy should be -1. Well, you have to give it some thought, really. You might think, well, let's make this guy on the bottom -1. The problem is, if I call this -1, right, all the laws of math still have to work. If this guy on the bottom is -1, if I add 1 to -1, here I'll add 1 to it, I should end up with a 0, and I do not. So that's a problem. The laws of math still have to work. If I use this top guy as -1, I will do that. Let's assume the top guy is -1. Again, if I add 1, I should end up with 0. Let's see if I do. So 1 plus 1 is 2, so 0 carrier 1. 1 plus 1 is 2, that's 0 carrier 1. 0 carrier a 1. 0. Now I'm only working with 4 bits, so the last one gets carried out into Neverland there. It just gets bumped off into outer space. So in fact, adding a 1 to 1, 1, 1, 1 gives me a 0. So we better make this -1. And likewise, this guy has to be -2, because if we add 1 to -2, we should get -1, and we do, and so forth. This should be -3, -4, -5, -6, that's -7, and -8. On this slide, I have rearranged the chart from the previous slide so that you see all of the positive numbers up on top. These are all, of course, my positives, and all of the negative numbers on the bottom. And just to jog your memory, since it was so long ago, this first bit is all ones here. This 1 in this first column right here means that it's a negative number. This 0 in the first column, or most significant bit, means it's a positive number. So what is the process, and this is an important one, what is the process of going from a positive number to a negative number? So for example, let's take a number like 4. The number 4 is 0, 1, 0, 0. How do I know how to represent that? There must be some mathematical operation of figuring out how to represent that as a -4. How do I convert +4 to -4, in other words? Well, it's a 2-step process. The first step is called take the complement, or first complement. Now, the complement of a number is just switching the zeros to ones and ones to zeros. I'm just flipping all the bits. All my zeros become ones, and all the ones becomes zeros. So this is the complement right here. The next step is called the 2's complement. I don't know why they call it the 2's complement. The 2's complement is done by taking the complement, which I'm just going to copy down here, and adding 1 to it. Now, I know I'm making this seem complicated, but it's really not. You just flip all the bits and add 1. That is called the 2's complement. So let me add 1, and I have 1 plus 1 is 0, carry a 1. 1 plus 1 is 2, so that's again 0, carry a 1. I have, bring down a 1, and then I have a 1. So apparently this number is -4. Remember, I started with a +4, and I wanted to find out what its negative representation was, and apparently it's this. Well, let's check on the chart. Did we get it right? We got it right. All right, let's pick a negative number and see what the positive representation is. So I don't know, let's pick something like -6. So I'm going to write it up here. Here's my -6. it is 1, 0, 1, 0. Again, that's -6. I'm going to take the ones complement. The good news is the exact same process. So 0, 1, 0, 1. That's called the ones complement. I'll just copy it right down here, 0, 1, 0, 1. And I'll add 1 to it. Same process, 1 plus 1 is 0, carry a 1, 1, 1, 0. That is it. Apparently, this number is +6, right? I took my -6 and took the 2's complement and I got +6. I don't know why I'm saying apparently it's +6. It is +6. Of course, when we can look at the table, you already knew that a positive 6 was 0, 1, 1, 0. And there you have it. So if you have a positive number and you want to represent it as a negative number, you flip all the bits, you add 1. If you have a negative number and you want to represent it as a positive number, it's the exact same process. You flip all of the bits and you add 1. That's it. Let's do a couple of examples of adding binary numbers using 2's complement if needed. Well, so here I have 2 positive numbers, and if I add them, I can just add them using regular binary addition. No reason to convert them to their negative versions. So for this example, let's assume that we're using 8-bit signed numbers. So to represent a 6, that is 0, 1, 1, 0, right? The 1's place, the 2's place, the 4's place, the 8's place. But let's again assume that we're using 8-bit numbers. So I'm just going to fill in 4 more zeros, right? So that's an 8-bit number. Now let's represent a 5. So that, of course, is 0, 1, 0, 1. That's a 5. And again, I'll fill in all the leading zeros because we're making 8-bit numbers. So if I just add them up, I don't want you to think that I'm adding a 1 there. So if I add them up, I have 1, 1 plus 1 is 2. So that's a 0. Carry a 1, that's a 1. And then, of course, I have all of my leading zeros. And that is the number 11, right? The 1's place, the 2's place, the 4's place, the 8's place. That's 8, 9, 10, 11. So it works. No reason to convert them into their negative values using 2's complement. All right. Let's do one last example of adding binary signed numbers. Now, in this case, again, let's use 8-bit numbers. In this case, I have a negative value here. So how do I represent a -9? Well, in order to represent a -9, you first have to make a +9. Again, I'm using 8-bit numbers. So all zeros, a 9 is a 1, 0, 0, 1. Again, the 1's place, 2's place, the 4's place, the 8's place. So yeah, so this is my +9. So to get a -9, remember you have to complement it. So I'm flipping all of the bits. That's called the ones complement. And now I have to add 1 to that. So I have a 1, 1, 1, 0, 1, 1, 1, 1. That is my -9, and maybe I'll write it off to the side there. 1, 1, 1, 1, 0, 1, 1, 1. That is my -9. And I'm adding to that plus 4. Well, that's a positive number, so 4 is pretty easy to represent. As a positive number, I'll just fill in the leading zeros, and a 4 is just a 1, 0, 0, right? 1's place, 2's place, 4's place. And now I just do my regular addition. So that is a 1, 1, 1 plus 1 is 2, a 0 carry a 1, I have a 1 there, and I have the rest I can see are all going to be 1s. Is that the right number of 1s? I hope so. Do I have 8 bits? 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's it, and that is my answer. The answer should be -5. And to prove that that's -5, again, I could take the 2's complement. Oh, let's do it. It's just so much fun. So I'm going to take the 2's complement of this. So again, I'm flipping all of the 1's to 0's and the 0's to 1's. So I had 1, 2, 3, 4, 5, 1. So those are my 5 zeros. 1, 0, 0. And that's my 1's complement. And if I add 1, I should get my 2's complement. So that is a 1, 0, 1. And all the rest are zeros. 0, 0, 0, 0. This is my negative, well, actually, this number is +5. I know it's a 5, right? That's the 1's place, the 2's place, the 4's place. So yes, this is a 5, which tells me that this guy up here is a -5. So this business on the bottom, just let me be clear. This is not the answer to my problem. This is the answer. I just took the 2's complement to get this guy down here just to make sure that this guy up here was a -5, right? So clearly this is the answer. I just did the 2's complement to show that that must be a -5. All right, it's as simple as that.